the time is up, but I'm going to just take it a little bit easy and allow everyone who's a little bit late maybe and just join everything, the Zoom or the Twitch channel, and just get something to drink, lean back, put the monitors in the perfect angle, and whatever you need, and I will start the presentation in maybe 1.5 minutes or so, and then it will go on for a while. I estimate maybe 2 hours, maybe a little more than 2 hours. And of course, everything is recorded and is going to be provided after the fact as well. So in case you have to run away because you have something important like a meeting, or you have to go to bed or get something to eat, go ahead. It'll be recorded. You can see it afterwards anyway. Or you can just come back after a break and, I will keep going here. I will mention it in the presentation as well. But if you have questions, fire it away in the chat if you're on Twitch, or in the Q&A thing if you're on Zoom. And I will try to get to the questions in line while doing the presentation, because it's going to be a long presentation. I can't wait to the end for questions, because, well, we will do questions in the end as well. But it's better if you have a question about what I'm talking about in the moment, ask it in the moment, and I'll try to get to that in the presentation, if I'm able to, if I understand the question, if I can answer it. Anyway, it's good to see so many people around. I understand that this is a little bit of a niche topic, and it's going to be maybe a little bit tiresome to follow along, but I'm going to do my best to keep it interesting. And I'm just have to move around a few windows on my screen. So I'm going to start the presentation in a few seconds, and I hope everyone is ready. Let's do this. Hello and welcome back. This is part 2 of Mastering libcurl. Today, well, I am still Daniel Stenberg. I work on curl. I work for wolfSSL. That's my site, and the image here on screen in the presentation is actually where I'm sitting right now, from a different angle, from a different time. But that's my workplace, my office here in my home in Sweden. And this setup today is actually very similar to the one we had for the part 1 on Thursday. It's live streamed, so you can follow along on Twitch and in Zoom, and it's expected to last a little bit over 2 hours. We'll see how long it's actually going to be. And it's, of course, recorded, so if you miss a few parts, you can see the recording after the fact. It's going to be available on YouTube as soon as possible after this. You will see a lot of stuff here that I've never presented before. So, and I've written a lot of new materials. I've worked a lot on the slides. So I hope that you will appreciate it and learn something from it. And there might be some mistakes, but we'll fix that as we go. Use a window big enough to make sure that you can actually read some of the source code, because I'm going to show a lot of examples and talk about code. So there will be some, 20, 25 lines of source code snippets on screen. And of course, all the source codes that I'm showing in these slides, all the examples are provided in this Git repository. The URL on the screen, github.com/bagder/mastering libcurl. And you can go there and get the examples and, copy and paste from there if you want to, or if you want to follow along, if you want to go back and check and whatever. It's like almost 50 examples, I think. Small ones, but still. So if you have questions about anything I say or related stuff or whatever you can think of when I'm talking about these things, just ask. The questions, of course, will not be visible on the screen, and I'm not going to have the audio from anyone while I'm talking. So just if you're watching this recorded, there might, of course, be, I might sort of embed answers and questions that are not visible. But hey, we can work it out. So today, Mastering libcurl, the first part, I talked about these things. a lot of things, you know, general things, the project, getting libcurl, building libcurl, how the architecture, how it works, fundamentals around transfers, getting handles, doing things, you know, synchronous transfers, as non-blocking transfers, and setting up things when you want to do transfers with libcurl. Today, I'm going to dive into more options and more fun stuff you really want to do when you want to do slightly more advanced things with curl. More on controlling the transfers, the share API, how a bunch of TLS options really that you might want to fiddle with when you do libcurl transfers. Things about proxies, HTTP, of course, being one of the primary protocols that people are using libcurl for. So I'm going to get into a whole range of HTTP specific options that you want to use, you might want to use to craft your requests and transfers to be exactly the way you want them to be. Then related, the headers API, as how you can get HTTP response headers back into your application in well, different kind of headers. Not different kinds, they're all HTTP headers, but still, I'll tell you about it. I will explain the URL API and how it works and how you use it. I will talk very, very briefly about WebSockets because I already did a whole separate video about it, but I will just mention that again. And then just a few words about the future, I'm not going to tell you what it's going to be like because I don't know, but I'm going to tell you something about how I view the future. So we stopped with an intermission in part 1, and this is now the continuation. Pretend that we are still talking about easy handles, multi-handles, easy curl, easy perform. You know, we were setting up transfer, we're doing transfers. Transfers are what you do with libcurl. Internet protocols specified with a URL. We have a lot of callbacks to do things. Yes. So we are going to talk about more stuff about how you manage the transfers, how your app can control your transfers, like this silly image here on screen. So let's dive into this. And I want to talk about what and how to store downloads to start with. Because, of course, downloads is, I mean, transfers are either uploads or downloads, right? Uploads send stuff to the server, downloads get stuff from the server to your machine. So how do you store things? When you want to transfer whatever data it is, you know, want to download a tarball, an image, a firmware, a map, a music, a movie, something, you need to store it somewhere when you download it to your machine. And libcurl typically does not store anything, actually. It just invokes a callback and lets your application do what you want with the data. It calls the write function. And, you know, is it a read, is it a write? From libcurl's point of view, it gets data in what it wants to store it locally. So it wants to write it. That's why it's a write function. So the application provides a write function when libcurl wants to write the data, store it locally, it calls the write function. Not the wrong one, the right one. So it also, in the same manner as all callbacks in libcurl, it provides this data pointer as a custom pointer to the callback. I'll show you in a few seconds on exactly, but we talked about this in part 1. The default write function, which is actually there, if you don't set a write function by yourself, libcurl will default to fwrite, and it will default to fwrite to standard out, which basically is never what you want. Because why would, I mean, when you write an application, you very rarely actually want to send the data on standard out just there in the terminal. But still, that's the default. That's what happens if you don't use the callback. So use the callback and use the right data to make sure that the callback gets the pointer you want it to get. And importantly to know here is that the function is called none, one, or many times. You don't know how many times, right? Because if it's it's a really big file, it's going to be called on and on and on. Maybe it's a streaming service. It never ends. It could be calling this, you know, indefinitely forever until you just stop. Or it might be a failure. It never gets called. And you know, network conditions will also affect it. So maybe it will be called many times with small chunks of data or fewer times with bigger chunks of data. You can't make any assumptions really. And when it gets data, it gets from 1 byte up to 16 kilobytes of data per call. And you know, that's the maximum number of data that it gets per call, because that's limited in the ABI. One of these days we might actually up that, but still that's how it works now. So it'll get data during the data transfer. And you don't really affect, and you can't really change. Well, you can affect it, but you cannot really assume that you know the amounts that it will get. It will just vary. So your callback then gets data from libcurl, deal with it. And then when the callback is done, you return a return code, of course, as any other function, right? And for the write function, you return the number of bytes you dealt with. If you get 125 as a number of bytes in, you return 125 to tell libcurl that, hey, I dealt with 125 bytes in my callback. And of course, if you don't return 125, libcurl will consider that an error and it will record. Sorry, it will return an error. There are a few other magic return codes too, but the basic stuff is that you return the number of bytes you dealt with, which should be the number of bytes you received. Here's a little example. It's just a silly write callback example, and this this is the same example I think I showed before, right? It's a write call. It creates its own struct here. It's just a pointer and a size, and in the write callback here we call it write underscore CB as for callback. It will just receive the data, reallocate a memory area, and copy the data into that memory area, and it will reallocate for every invocation. Very inefficient, but it will just add data to a reallocate memory area that will grow and get more and more data. So this is really not a way to manage a really big download, but if it's a really small download, it might be good enough for you. So it'll just store the received data in a memory buffer. Kind of convenient sometimes, if that's if that is what you want. Right, so that is the basic. This is an example of a write callback. In many other times, you don't want to store it like this in memory because maybe it's too big. Maybe it's you need to check the data somehow, you parse the data, manage the data somehow, or maybe you want to pipe this data into another program or into another process, or who knows what you want to do with the data that you're getting. And I mentioned this in part one, and it's worth mentioning again that when libcurl is getting this and downloading this, it doesn't know at all what the data is. You know, it's just a byte. It's just a byte stream for curl. It doesn't understand the data. It'll just provide it for you. You have to decide what to do with the data, check the data, investigate, is it the right format, blah, 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 whatever the data is. When downloading, curl also supports a lot of different compressions. And there is no compression at all by default because, as mentioned before, curl does basic stuff by default. Basic doesn't imply compression, so it'll just ask for things. It will not do compression. And if you want to do HTTP compression, and I will get into HTTP compression a little bit later with slightly more detail, but it's important to remember and know that HTTP compression is only for downloads. There's actually no HTTP standard for doing compressed uploads. There are and have been conversations and discussions and thoughts on how to fix this and provide this in the future, but right now there is no upload compression standard for HTTP, so only for download. And if you're using HTTP2 or HTTP3, there's something called header compression, but that is sort of built into the protocol, and it's not optional, and there's nothing you can control. And really, curl is hiding that for you, so you won't really have to think about it, and you won't see it. You might just be aware that it'll happen over the wire magically without you caring about it or having to care about it. Anyway, for HTTP, to get data compression, which you might want to enable, you set this curl opt accept encoding to just two double quotes. And this looks really weird, right? Why is compression called accept encoding, and why just two double quotes? And both parts have a historic explanation. First, accept encoding, that's the way you do it with HTTP, really. That's a header. And it's a weird hack that has become a de facto standard on how to do it. Is actually not, it wasn't the intended way to do it, it just grew into this. So therefore it's a little bit of a mistake that this is the way to do it, but this has become the established way to do it. And so that's why also the libcurl option is called like this, and not compression or something more that will probably sound better and be more understandable. And the double quotes thing here, that is an empty string. That's a magic, special magic clue to curl. If it's an empty string, it means try to use all those compression algorithms that you support, however many they might be, and whichever they might be, which is cool because that sort of removes that knowledge from the application. You just have to set this, and you let libcurl deal with it. Whatever sort of algorithms libcurl supports, it will use them. You can set a specific algorithm here with a name in the string, but that also makes it much more difficult, but because then you need to know that is what libcurl supports, and you need to know that is sort of what's the preferred algorithm to use against this particular server that you're going to talk to. So typically you want it done like this. If you're talking SSH instead, that is SCP or SFTP. There's a separate option to set called SSH compression. And for SSH, it's a completely different protocol sort of property. And that compression is done over the channel for everything. And I should just mention that the accept encoding thing for HTTP, it's typically okay to set it for whatever you want to do, and it will do compression if it can do compression, and otherwise it won't. So it's more of an ask. So generally you can set that to a lot of requests, and it'll get compressed and decompressed by curl if that is what the server supports. Otherwise you won't get it compressed. But in the end, ask if compression just means that it will be compressed over the wire, right? libcurl will still uncompress it for you by sort of transparently. So the data stream that you get as a client, as an application, will still be the same, compressed or not. Compressed will just mean that you send less data over the wire. It'll be a smaller data transfer. It'll use slightly more CPU, but the data transfer will be smaller. And also, of course, beware of the thing they call decompression bombing. This is basically if you're using compression, if you're asking for compression, something big in the other end is compressed to something smaller, right? And that small thing gets over the wire and it gets decompressed in your end, in the client side, and it'll decompress into something larger. And there are combinations here where something very small can expand into something very large, right? And some of these algorithms, they can actually expand pretty much a few dozens of bytes can expand into gigabytes of bytes when they decompress. So you can't assume that you know how much data you get when sort of if something just sends you compressed data, it might decompress into something huge. So you should just be aware of that if you're doing this and you have an application. But the write callback is called the same way, because the write callback is called with decompressed data. So having compression or not doesn't really change the data that arrives in the write callback. And this is, of course, the sort of the automatic compression decompression. You can, of course, still also just download a tarball or something that is compressed and just pass the compressed tarball to the write callback. That is also perfectly fine. Then you just don't ask for accept encoding, just get it, and it'll just be sent as is to the write callback. Anyway, here's the example then, how to enable compression. This enables HTTP compression. And in this case, we see this easy setup, sets curl opt accept encoding to a blank string, set the URL, in this case to the curl website, do a perform. And in this case, it will do a transfer that is, I think it's less than half of the size uncompressed. So a win if you want to transfer smaller amount of data. And of course, that's download, right? So if you want to download multiple files, I want to iterate this, how important it is, reuse easy handles and call curl easy perform again if you want to do serial transfers, right? One and one and one and one and one, just over and over and over. Reuse the same easy handle. And if you want to do many in parallel, add many to multi-handle, but there as well. When you're doing multi-handles, it's less important, or actually it's not important, to reuse easy handles, because then the caches are stored in the multi-handle and not in the easy handle. So you can still take advantage of the caches by using the multi-handle. So then you can kill and start new easy handles without suffering any penalty. And if you do multi-handle transfers, that is many parallel transfers, they can be made multiplexed, which means that they can reuse, sort of, you can do many transfer over the same connection. And I'll get into some details about that. And of course, if you run transfers in a single core, since again, libcurl does transfers single threaded, right? So in a typical case, you run curl in a loop, or you do curl maybe you do curl easy perform, one blocking synchronous transfer. It'll transfer whatever really fast, but still just a single core. If you're CPU bound, maybe you have a really, really fast network, and maybe you could be CPU bound. You can only download so much on one CPU because it'll just eat all the CPU. Then you can, of course, start the same thing on multiple CPU cores or threads and transfer more data in separate threads, of course. And curl, of course, supports that I will talk more about threads later, but you can easily just run independent transfers in independent threads. That's easy and sometimes preferable. And when you want to download stuff, I talked about the decompression bombing, that sometimes things get much bigger than you anticipate. And really, some transfers you do over the network, you just don't know. Well, first, your application might not know ahead of time this presumed size of the remote resource. Sometimes the protocol says, I'm about to transfer this big data, this amount of data. And then oh, that's too big, I don't want it. Or maybe it doesn't say that. Maybe it just says here, the data starts here, and it'll just keep sending, right? And it could be a never-ending stream that never ends. That's big. Could be big. If it's fast, never ends. And when curl downloads something, libcurl downloads something, it has no default size or time limit. If you ask it to download something, it will keep downloading that until it's done or until it fails. But we provide this option called max file size large. That's a way for an application to say, don't download the file if it's bigger than blah, which of course then can save your application from maybe not storing too much crap, because if it's bigger than this particular limit threshold, something was wrong and you rather not have it just take a lot of space. And of course, you can set a timeout, as in my transfer is only allowed to take this many milliseconds before we consider it bad, wrong, get out of it, cancel, stop it. Which might be hard to set a fixed time limit, right? Because sometimes you have a slow transfer, sometimes it's really fast. But still, you have that fixed time limit to set if you want to. Or you can also limit the transfer, for example, in the write callback, right? Because the write callback gets all the data. You can easily count the data there. So if you write, and you just increment a counter there, or you see that, oh, now my counter has reached 20 gigabytes, return an error, it's too big. Convenient way to do it. Another regular way to monitor transfers and to do custom things, to maybe have a custom timeout in some way, is to write a progress callback that is called just repeatedly with progress information about how much has been transferred. And you can have that return an error too at some point to stop the transfer because of you have reached some threshold or limit or done something that you're not happy with. And you can, of course, ask a server to continue a previous transfer or just get a part of it. And libcurl has that resume from large. It's called large, and the suffix there is because it's a large value, because if libcurl is such an old thing, right? So we started out with one of those without a large, then you could only have a 32. Well, on some platforms back then, you could only have a 32-bit value, which was stupid. And you can set a range, for example, like this. If you want to get a page from a URL, well, in this case, of course, I made up this URL doesn't actually exist. But if you would get it, and in this case, there's a curl up the range option here that says you can ask for byte range 200 to 999. And that's actually included, right? So it's sort of byte offset 200 to and included byte offset 999. You ask the server, only send this back to me. And if it complies, you only get that chunk of data back. So what's that? 800 bytes. And not, even if that page is huge, you only get those 800 bytes. Which of course is cool if you want, that they were broken in your previous transfer, or you just want that updated, or for whatever reason. Maybe you do one of these funky transfers when you have 22 threads and they're all downloading different ranges from the remote resource. And when you download things, or when you ask libcurl to download something, it has a buffer size internally. And the buffer size, first of all, is 16K by default. 16K is not a lot by today's standards, but it also matters a little bit how many 16Ks we're talking about, right? If you're doing 2,000 parallel transfers, maybe 16K is enough. Maybe it's not. Maybe if you have a small system, then maybe 16K is big. You decide. Anyway, you know that it's there. And the buffer that we're talking about here is a buffer that is allocated and associated with an easy handle. So each easy handle, when in use for a transfer, it has a download buffer. Is actually allocated at the first time it's needed, and I think it's freed as when the transfer is done. So it's only there while there is an active transfer. So that's good, because then it's not wasting memory when you're not doing transfers. But anyway, you can ask libcurl to set different sizes. So you can ask it nowadays. You can just pump it up to 10 megabyte buffer if you want to. And why would you want to change the size of the download buffer? Well, the download buffer is clearly affecting the transfer speed, because the buffer is pretty much what you're, in most cases, a buffer that you get data into when you get transferred chunks of data, possibly from the kernel, possibly decrypting with TLS, and then putting it into the download buffer. By having a larger buffer, you can put more data into the buffer before you have to call the write callback, right? So pretty much you can get larger chunks of data from the from the kernel. In a modern machine, it rarely has any particular effect as long as you do network transfers over a actual network, because usually the network is the limiting factor. Even if you have really fast networks, that's usually the limiting factor. But there are cases, for example, if you do a download from a local host, when there's just just a TCP stack, there's no actual physical network involved, then the transfer speed could grow really, really high, and then you will see a notable difference in between small buffers and big buffers. Maybe 10 megabytes is a little bit excessive. Maybe you never really actually need 10 megabyte. I don't know. You can experiment yourself for your particular transfers. But you can just know that the curl tool, for example, it sets a 100K download buffer by default, simply because I realized and noticed when I did some measurements when doing localhost transfers, that suddenly boosted them quite a lot compared to the 16K default. But maybe it wasn't really worth bumping even more. Or maybe it is. Maybe I should do some more tests about that going forward. When you want to do transfers in the other direction, right? Uploads. We want to send stuff to the server. How do you do that? I talked about the write function when we want to store data. Conversely, of course, there's a read function when we want to read data to send away to the server. And of course, again, then if we return an error, we stop the transfer. But pretty much all the callbacks are like that. If they return errors, the transfer stops and it'll return, aborted by callback, which is convenient because you can use that as a way to stop transfers. And the read function, it works like this. And here again, I have a little weirdly named struct called write this when it's actually a read callback. But anyway, that's the read callback called read underscore CB, CB again for callback. And in this case, the read callback gets called by libcurl when it wants to, hey, application, give me data to send. And it gives the application a buffer pointer and a size of that buffer. So in this case, and this is modeled after the fread function. Again, not the most convenient API actually, but hey, I did this a long time ago. Bear with me. So anyway, so basically it says, please populate this buffer with data up to this amount, and then tell me how much data you actually put in that buffer, and then we can upload that. So in this case, it actually checks how much data can we still upload, and we copy that much data into the buffer, and we return that amount. It's not that complicated. Maybe it sounds more complicated. So the actual use case of this example then pretty much sets things up to use the read callback. It has a data pointer and the length of the data. Sets the URL, asks, hey, I want to do an HTTP post, because in this case, it obviously just used HTTP post to do an upload. And then it sets the read function callback. It sets the read data pointer, a pointer to our own little struct here. It enables verbose because why not? Verbose is good. You want to have a lot of details. And then you do the perform, man. And of course, it will then call the read callback over and over to get data to send until the callback says, I'm done, I return a 0, we're end of file. And when we're end of file, we also know that there's no more data to send. But the operation is complete. There are other ways to do uploads, and I'll talk about more HTTP specific ones later, because HTTP has more. But upload in general is a concept for many protocols, right? Almost all protocols curl supports have an upload concept, so you can send data to servers using a lot of different protocols. Right, and these are the two other more HTTP specific ones, and we'll get into those. Who knows? In half an hour, 45 minutes. And if you want to do multiple uploads, because why not? Again, you can, I mean, you want to reuse it, I was going to say, but you can of course mix uploads and downloads however you want, because they're just transfers, right? And for libcurl, it's transfer either way. You just have to set the right options to do an upload or a download. And when using the multi-interface, you can of course do them in parallel simultaneously at the same time. Uploads and downloads, it doesn't matter, or you choose. And the same rules applies for exactly as I told you about downloads. You just reuse these handles, and if you want to do them in parallel, you do them with the multi-handle. And uploads can of course also do multiplexed transfers if you use H2 or H3. I talked about the download buffer size when you're downloading things into a buffer that then gets called, delivered to the right callback. And conversely, there's a similar thing for uploads. So the upload buffer is sort of the buffer libcurl hands to the application, says, here, give me data for me to send away to the server. It's the upload buffer. And it has a default size of 64K for some reason. So 4 times the size as the download buffer. And again, this buffer also only is allocated on demand. So it isn't actually allocated until there's an actual upload that is happening. So anyway, it is up. You can then also change this size if you want to. If you're doing uploads over, again, localhost or a really, really fast network, maybe you want to increase this size. It has a smaller maximum for some reason. Just history, just has happened to be like that. If you have a particular use case, I can only encourage you to tweak these values and test them out in your environment to check and does it actually make a difference if I change them? Can we get it faster, slower, whatever? So I encourage you to try that out, because it's also fun. And of course, it might certainly affect the transfer speed that you can do uploads. And I mentioned multiplexing before, and I wanted to just make sure that we are all understanding this and talking about the same thing here. So multiplexing is something that curl supports, and that is when you do a lot of more than one transfer using the same connection. So 1, 2, or more transfers over just one connection. By default, libcurl will always do separate transfers over separate connections, because that's the sort of old style simple thing. They're all independent, but pretty much it works like this. So when you set up a connection from the curl client here to the server over there, and you want to do multiple transfers, so you do a first transfer in one connection, and you do a second transfer in a new connection, or you do a third in the third, and a fourth in the fourth. So there's just one connection per transfer, unless they are reused, right? So you could do them, if you do them serially, they could reuse the same connection. But by default, if you do 4 connections at the same, so if you do 4 transfers at one time, they will by default use separate connections like this, 4 separate connections. But if you instead ask for multiplexing, you can make them, if they go to the same server, you can make them use the same connection instead, if the right conditions apply, because it'll use the bandwidth better and fewer resources and a lot more fun. So then instead of going all the 4 transfers using the connections by their own, they're reusing a single connection. So 4 transfers over a single connection. And of course, multiplexing is only there, and it only works if you have HTTP 2 or HTTP 3 transfer to the server. And yes, some additional requirements are also required, because again, multiplexer means that you have 2 or more transfers going at the same time, right? And the only way to have 2 or more transfers at the same time with libcurl is when you're using the multi-interface, the multi-handle. So that's the only way you can do more than one transfer at the same time, right? On the libcurl's control, sort of. Also, you have to enable multiplexing with this option. It's a curl multi-interface option. It's called pipelining for historical reasons, but you enable multiplexing with that, or you ask for multiplexing. Please use multiplexing if you can. And there's a maximum number of streams, and streams is a transfer over a connection. So there's a certain number of certain number of transfers you can do over a single connection until curl would start a new connection for the next transfer. And connections can also, from the server side, they can basically say, hey, I don't want any more transfers over this connection. And then the next transfer curl will actually use the next connection instead, or create a new connection. It's a bit complicated, but I'm just mentioning it because it's there and it sort of pops up every now and then. Usually, and the idea here is that multiplexing or not is not really visible to the application. It's done transparently, and curl will just do whatever it can do according to the instructions. But from the application's point of view, it just does internet transfers, right? Maybe they are multiplexed, maybe they are not. The data is going to go in either direction the same way. The API works the same. It appears the same. But if they are multiplexed, they're just going to use fewer connections. And it can multiplex. Look at this. It needs to use a multi-handle, so the transfers has to be done over the same multi-handle. It needs to use the same HTTP or HTTPS sort of scheme. And if it's HTTP3, it can only be HTTPS. But if it's HTTP2, it can be either HTTP or HTTPS. It has to be the same port number. It has to be the same host name, and it has to be the same HTTP version. And if all of those are that's true, then it might be possible to do multiplexing. So typically, of course, then if you set up a transfer, if you want to do X number of transfers to the same host, and you happen to use HTTP2 or HTTP3, and you can get them in parallel, that might very well do multiplexing. Okay, so I talked about doing transfers and download, uploads, and I also mentioned that transfers typically just, they go on until they either fail or succeed, the entire transfer, and then it's done. But what happens, or how do you do it when you realize that maybe I need to stop this transfer because something is wrong, or I don't want to let it go on anymore. It took too long. I got wrong content. Someone told me to stop it. How do you stop a transfer? And that is fun because, as I mentioned many times here, the curl easy perform makes a synchronous blocking transfer until it returns, right? So it blocks the thread. So how do you stop the blocked thread from continuing? First, of course, there are several timeouts, numerous of them. So you have, the maximum timeout, you have a connect timeout, you can have low speed timeouts. There are several different timeouts that you can set and sort of put the frames around. This is what I allow my transfer to, this time it's allowed to spend in these different states or to reach these different conditions. Anyway, so that's one way to make sure that, hey, it'll never go on longer than 27 seconds because I've set that hard limit. And you can, as I mentioned, and this is actually the best way to always remember that you can return errors from callbacks, and there are numerous callbacks. I think it's like 20 callbacks. All of them can return errors. Something is wrong, return error. If your write callback returns error, it'll stop. If your read callback returns error. So be really careful with threads, because typically you don't stop transfers with threads in libcurl. I mean, there's no stop the transfer call from another thread, because that's not how you do it. If you want to do it with threads, you typically set some kind of mutex or some kind of variable that you then check in a callback somewhere. So maybe the progress callback is called repeatedly during a transfer many times. So in the progress callback, you can, for example, check a variable, the stop variable. And if that is set true, I can stop. And then you can have another thread set that variable. Maybe that's up to you, but that's one way to do it. And if you're doing a multi-interface transfer, you know, many parallel transfers driven with the multi-interface, you can just remove an easy handle from the multi-handle at any point in time. And then, of course, that transfer gets removed from the multi-handle, and then it's not part of the transfer machine anymore. So that's sort of, yes, then the transfer just stops, and it's, yeah, it ends there. But maybe you just want to stop a slow transfer. You know, you've all seen things, and you know, we've all used browsers for a long time, and sometimes maybe more in the past and on the modern web. But you know, sometimes when you want to download something huge, you just realize that over time the download just goes slower and slower, and suddenly it seems to not download anything anymore. Just go down to 0 byte per second, and it just sits there, or 3 bytes per second for a very long time. Whatever, and that's kind of annoying, right? And that's certainly, I mean, there's nothing wrong here. That's how the internet and transfers just work by design. First, of course, since I just got a question, that's why I sort of stuttered here. The question is basically, so if I want to do transfers from many threads, how do I manage connection cache and connection pool? And a long story short, there's a supposed method, but it doesn't really work. So the idea here that and we'll get into that in a few seconds. But since I got the question now, there's a share API that should allow you to share data between easy handles and easy transfers, and that can share the connection pool as well. It just happens that it doesn't work in a multi-threaded way. I'll get back to that. Right, so in slow transfer, then, I mean, it can go down to however slow you, I mean, you've seen everything, but in libcurl, we provide options to say, if the transfer is slower than this many bytes per second, and it is this slow for this amount of time, kill it. So it's below, you know, if it's slower than 30 bytes per second for 22 seconds, kill it. And we support this with the curl opt low speed limit and the curl opt low speed time. Those are two options. You set them, and bam, you make sure that the transfer is either faster than that, or if it is below the threshold for that long time, it will get killed. Just a way for you to make sure that if something goes if it degrades to that level that you can't accept it, it will get killed. Or pretty much the other way around. If you and this, of course, on many machines, we do a lot of network transfers, right? And maybe we do a lot of network transfers in parallel, different applications, different threads, different purposes. And maybe you have a limited network capacity. And sometimes when you do a lot of things over the network, there will be a struggle for who gets to do what over the network, right? So maybe at sometimes you want to say that, hey, my transfers are not that terribly important. It's enough if they take a maximum of this amount of data per second, just to allow the rest of your system to get more data out or in, or there could be also many other reasons why you want to do this, but this is one reason. And libcurl then provides an option for you to say, hey, don't spend more, also don't do the transfer faster than this. And bear with me here, because this is it's an attempt to keep the average speed be below this threshold over what I call a period of time, which is not specified. So I'm giving you all these caveats here because this is not an exact science. It's hard to make sure that, and what, so it means that it will do short bursts that are faster, but over a period of time, the average is meant to be at max that limit you set. Like this. This example is, I mean, as you can, if you start from the top here, I actually made up totally arbitrary random maximum numbers here, but it says a maximum receive, that is number of bytes per second that it allows the transfer to use, or yeah, that's the maximum transfer speed to receive, and the maximum send is then the maximum transfer speed to send. And in this case, the rest of the operation is a download. So the send operation, of course, is not going to limit much. But anyway, I just wanted to show both options in the same source code, because I mean, you could as well also do an upload. Maybe you do, and for example, when you're doing HTTP, you could do upload and download pretty much in the same operation, right? So the same transfer could have both upload parts and download parts, and then it could make sense to set them. So that's how you then ask curl, don't transfer data faster than this, because for some reason that makes sense. I talked about the progress callback before, and there is a built-in progress meter in libcurl. It's, I would say, maybe one of the less clever ideas I had when I started this, or actually it started out with the progress meter was made for the command line tool when I started everything. And then when we converted things from the command line tool into a library, we brought the progress meter into the library as well. I think that was less clever, but still that happened, and it's still there. So it has a built-in progress meter that can be displayed on standard error. I don't recommend you to use it. It's much better for you to manage progress meters yourself, which in the way you think is most suitable for your application. So the progress meter is disabled by default. And this is also, it has this crazy name that it's reversed. So it's a negative option, no progress. And you set the no progress to 1 to disable it. So you enable the no progress to disable it. It's you know, it hurts your brain to think about it too much, so don't. But anyway, you should set a progress meter, and that progress meter can then set an error to stop a transfer. That remark there is totally out of place. Return error to stop a transfer, because the return error to stop a transfer is about the progress callback, and there's no progress callback on this slide yet. I will talk. So this is how you enable the progress meter if you want it for your libcurl transfer. Pretty straightforward. In this case, then, so you set it to 0 to enable it. Kind of the reverse. Yeah. I'm not super thrilled about that, but I wanted to get into the progress callback, because the progress callback is the way you really want to do a progress meter, the sort of the better way, the correct way, the way you really should. The other one you can forget, and then instead you keep track of the transfer yourself, and you and the fun part about the progress callback is when you use it with the easy interface, you know, the curl, you do curl easy perform, blah, blah, blah. It will also call the callback when the transfer is idle. So even if nothing is being transferred, it will call the callback every now and then to tell you, hey, we have transferred this much, because it makes it easy for you to do a progress callback that is also updated even when no data is being sent. Pretty much like a progress meter is supposed to do, I guess. So it works like this. So here's a progress_cv, progress callback function. It has this prototype where it receives a number of numbers. It receives 4 numbers: the download total, download now, upload total, and upload now. where download total and upload total is the expected total file transfer size, and the DL now and UL now is the number of data that we have transferred so far, download and upload, or so in both directions. So, and it gets, so this progress callback gets called with this information while it's transferring very often, but if there's no transfer, roughly once per second. I say roughly because it's meant to be about once per second, but it's not going to be an exact science here. So, and the yes, and it has this, the first argument here, the client P, is again the custom pointer passed in from the data argument that you set in setup. So anyway, yeah, this is then up to your application to decide what to do with it. Show it on the screen, and if you just for some reason deem it being slow, fast, wrong, return an error and the transfer will be stopped. And this is of course how to use it. In this case, I have this struct progress thing that I'm just showing you how to use it. It sets a struct with some field members. It sets the progress data pointer to the struct, pointer to the address of the struct, and it sets the transfer info function. That's the callback, the name of the callback, points to the function then, and it sets the URL. Maybe this particular URL is not the most clever one to use for this kind of example because it's really small. So it's not going to call the callback many times. It's just going to basically going to happen once or twice, if even that. But yes, that's how it works. Really easy and convenient. And again, I talked about timeouts before, and let's just get back to that because timeouts is important. So typically when you do a transfer with libcurl, there are no timeout. There's actually a few, very liberal one, like the name resolve has to complete within 5 minutes, I think, and stuff like that. You know, really, really long timeouts, probably much longer than most people actually want them to be. So there's this risk that if things are terribly slow in the other end, libcurl will just sit there and wait for it to complete for a very long time, and possibly never end because of a long time. Just a long time is no error, according to curl. So you really might want to narrow things down, you know, stricting things up a little bit. Then we have this curl opt timeout, and it has it exists in 2 versions. You'll see some of our timeout exists in 2 versions because we first created the one with integer whole seconds, and then later we realized that maybe entire, you know, just integer seconds is not good enough, so we introduced the millisecond versions of the timeout. So they typically come in a second version and a millisecond version. Basically, this is the longest time you allow the transfer to take, and if it takes this long, it will return an error. There's also this is the longest time we allow a transfer to spend until it has reached the connect state. So basically all these things setting up the transfer until it reaches a connect to the server, to the other server. So, you know, if the name resolve is too slow, if the TCP handshake is too slow, if the TLS handshake is too slow, so it takes longer than however long you want to set it to. If that takes too long, kill it, because obviously it's not going to work because you have higher requirements than this. So you decide. Or you make your own with the progress callback, as I mentioned before. It's a pretty convenient way to, so then you can add all fun conditions that you want, right? Because you can, all the numbers you get from libcurl, and you can add all your own numbers and time it yourself and add whatever, you know, outdoor temperature and shoe sizes of your visitors in your house, or whatever you want to add into the algorithm. So that's a lot about, you know, reading, writing, and controlling transfer speeds and timeouts and things. And once the transfer has been done, right, the upload or download, there are also, metadata from the transfer, traces, details that we remember that happened during the transfer that you can interrogate libcurl about after the fact. When the transfer is done, hey, can you tell me a little bit about things that happened in the transfer? Pretty much libcurl has that easy handle, right? And it remembers a few things about the transfer you just performed. So you can query it about things. And there are right now then 71 different options so that you can ask it about, like the size of the transfer, if in case you didn't count it yourself, and you can ask for, well, the speed, blah, 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 a lot of different things. And again, we have man pages for everyone. So there are 71 man pages just for the curl info variables. They're all curl info are the variables you pass into curl easy get info to get more, to get data about a previous transfer. Here's the list of them. As you can see, a whole lot of them. Things like, you know, which URL did it end up to on, how many connections did it use, how long, different timing information or different sections of the transfer. You can ask for the response code, download sizes, speeds. I told you that already. Yeah, so a lot of different things. And you use it like this. You can call curl easy get info from a callback, which is not really what you can do typically from call. Typically, we don't encourage, or rather we forbid calling libcurl from callbacks because it gets such a recursive craziness in our heads. But this particular function you can actually call from within callbacks. So a few of the variables then actually exist in callbacks, and they are documented like that. So you really should read up in the docs when you want to do that. But some of them are really convenient to get in a callback. And here's in this example, I just wanted to show you some ways on how you can extract things from a previous transfer. And this again has this third argument in the curl easy get info function is a type that depends on what kind of option you ask for, right? So the type, you need to read the man page so that you know what kind of argument to pass in the third argument in this function. Like if you check here, the curl info content type here in the middle of the source code, it gets, you pass in a pointer to a sharp pointer. So you get the pointer set to the content type of the previous transfer. The next one, the curl info size download t, it wants a pointer to a curl of t size type. So it stores the download size of the previous transfer. And the third example here, it gets the primary IP of the most previous transfer. Primary IP, the remote IP that we connected to when we did the transfer. And that too wants a pointer to a sharp pointer. And it sets that pointer to point to a string. So this is a convenient way for you to just get information about the previous transfer that maybe was not that easy for you to figure out yourself during the transfer. For example, if you, since URLs typically, like in this case here, you set it up to use curl.se. Curl.se resolves to, I think, 12 different IP addresses. So you don't really know which of the IP addresses curl actually used when it did the transfer. So therefore, asking for the primary IP in the end there actually tells you which of all those 12 IPs did it actually connect to and do the transfer with. Convenient thing. And as I said, a lot of those variables, I'm sure that we are going to add more variables to that list going forward as well. So it's really a good source of information. I talked a little bit about threading before. I'm just going to get back a little bit. I'm not going to spend a lot of time on threading because it's not that interesting. But typically the guideline says never share curl handles, any curl handle simultaneously across multiple threads. So you never use the same handle in multiple threads. at the same time. You can pass it around when it's not used, but if it's used, make sure that it's only used in a single thread at any single moment in time, because there's no mutexes or thread protections within libcurl. It just assumes that you're doing the right thing, so it won't check, protect, and sort of put any guardrails up. It'll just assume that you're handling it correctly. So it's perfectly fine to do separate libcurl transfers in separate threads, and it's sort of encouraged, and a lot of people are doing it, right? So you can do 100 threads with a transfer in each, and that works really fine if you just make sure that you don't share handles across threads. And you can also, and I will mention this in a separate thing in a few seconds, there's a share API too, that you can actually share data between easy handles even when they run in different threads. So you can also share a certain amount of data between handles even when they run in different threads, which is a convenient way to make if you want to make more, I don't know, high-end, more complicated transfer applications. And of course, multi-threaded, I mentioned this already, but let's say it again. If your transfers are CPU bound, if you can't transfer more because your CPU is at 100% and you're still not saturating your network, maybe you want to do another thread or another CPU core with transfers so that you can transfer more data. Who knows? These days you can do a lot of you have really fast transfers sometimes. And libcurl itself is, of course, I would say, pretty fast at doing network transfers. So you should be able to do quite fast network transfers per CPU thread and core. And as I mentioned before, typically all the libcurl API and operations are in the same thread, so it'll never do callbacks or surprise you from another thread. It'll all be in the same thread that if you invoke curl in a thread, it'll stay in that thread. You won't do any surprises. That about threads. Threads can, of course, be complicated, but as long as you just make sure, don't throw the handles around in multiple threads, and then you'll be fine. Error handling, then, of course, as you've seen, and I sometimes, I'm not sure exactly how to deal with it, but in a lot of my examples, I don't show error handling because I wanted to simplify my examples. So I don't show a lot of return codes, checking that the return codes are okay. But libcurl always returns an error if there's an error internally. So if you use libcurl function calls, always check the return codes. And we get a lot of questions from people who have a problem with libcurl sometimes. Oh, it doesn't do what I want to. And then I ask them, so what did it return? And then when I check, oh, it returned an error. Yes, and the error means that it was an error. And the error code is typically often describing what the error was and so on. So this maybe should have gone earlier in my presentation, but this is a key to making a sensible application using libcurl. Check the return code. Do that early on before you ask anyone what's going on. Check the return code, make sure that it returns okay before you sort of start to debug your application. And I mentioned it before, the error buffer, you want it, set it. And typically in libcurl, it doesn't have any sort of retry. So your application needs to do the retries or strategies around that. Curl will fail if it fails. If the transfer stops for some reason, if there's a protocol thing that says it can't continue, it will return an error for you. And you will deal with it or not. It's up to you. So curl will not retry typically. I say typically because there's a tiny edge case sometimes when it does, but I'm just going to ignore that and pretend it doesn't exist. And also, of course, one of the fun things with curl, if you use curl, the command line tool, is to use the command line tool to work out something that works for you and then convert that into source code as an embryo for you to start your libcurl adventures. So whatever you want to do with the curl command line tool, curl, blah, 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 a lot of command line switches. And when that command line works for you, you add -- libcurl and a source code file name, and it'll sort of spew out a source code skeleton for you to start working with. So, for example, here's my maybe not very, very creative example, but here you can see me adding just a custom header to a request, foo:\bar, the URL, and I want to save the source code to the file name --.c. And when I do this, of course, it sends the output to standard out. So a lot of HTML, blah, but look at that --libcurl --.c. This is how the source code looks. Well, this is the top of the source code. It's too big for me to show the entire thing. I just wanted to show you that this is the embryo for this is what that curl command line did, more or less, mostly more actually. So here's a good starting point for you to make an application that does the same thing as your command line just did. So a good list of options that the command line tool used. Maybe you want to do that, maybe you want to tweak it, and then go from there. I find it a really convenient way actually to convert, to get started and to convert that thing you got working with the command line tool. One of my favorite command line options, really. Okay, so as you can see, there are a lot of things to do with curl, and I'm going to take you through a bunch more, and I'm only a third through, and I'm already over an hour into this. So let's continue on. So there's a way to share data between handles, and with data, I mean caches and configs, really. We call that the share API. So there are caches and state kept per easy handle if you want to do them with the easy interface. And when you do easy interface transfers, you might want to share data, right? If you want to do one transfer and then another transfer, maybe they have something in common, and you want them to share a certain amount of data. And when you want to do that, here's how to do it. You create a share object. This is an object with data to share between one or more handles. And you decide what to share in this share object. And the data could be, there's of course a set of data that you can choose from, a number of different options that curl supports, and it's a growing number. And then you tell an easy handle to use that particular share object. And by doing that, that easy handle will share that data between the other easy handles that are told to use the same share object. And I'll sort of, just to illustrate what I'm talking about, because it might sound a little abstract and crazy or strange. But anyway, you can share stuff like cookie jar, that's all the cookies, the DNS cache, the connection pool, TLS session ID cache, the public suffix list data. You can share the HSTS cache, and more things going forward. Yeah, there's certainly a bunch of things you can share. So maybe you want to have your different easy transfers to share these data instead of having them all isolated, right? For example, cookies, that's one of the typical ones. Maybe you have a number of transfers and they actually are related cookie-wise. So why not share the same cookies? So then you make a share object, share the cookies, make sure that all the transfers use that share. Like this. Here's the share object A and the share object B. So, and I just made up 3 transfers that from the top, they use the share object A, and the transfers from the bottom, the transfer 4 and 5, they use the second share object. And just, it's a little bit complicated to explain for me like this, but as you can see, then they use a share object, and those share objects, they can then be specified to use a certain set of data and share a certain set of data. And the data that they don't share in the share object, the easy transfers will use privately, right? So you can, for example, if the share object A share cookies, all those 3 top transfers will share cookies with each other. But if they only share cookies, they will not share the DNS cache, or vice versa. And yeah, you get it. So in this case, yeah, I had some examples. So if you share cookies and DNS cache, and the second share the connection cache, so that's how it works. And you set it up like this. In this example, we create a share with share in it, and you will recognize a pattern here with the init and the cleanup and the setups. So we create a share handle, we set a share setup. So pretty much we ask share cookies in this object, share object. And then we create 2 easy handles. We set URLs for the 2 easy handles, and we, in both those easy handles, we say use this share object. And this share object, we share cookies, right? And then we perform transfers, 2 of the transfers serially here, and they will they use the same cookie cache, cookie jar. Yeah, so basically, if the first transfer gets cookies, updates cookies, the second transfer can take advantage of that set of cookies. And then we clean everything up, and in the end there we clean up the share as well, because of course otherwise, yeah, or you reuse it or whatever. I think you get it. Unfortunately, well, what is good is also that the idea here is that, of course, you can share these things across threads. So if you do share curl easy perform in different threads, you can share all this data between threads as well, as they are different. And that's a cool thing if you want to share your cookies between many different threads all doing transfers. And to do that, you have to set up mutex callbacks within the share. So you have because again, curl doesn't know about threads, but it assumes that you handle threads correctly. And if you set up mutex callbacks with the share interface, it will mutex and lock and unlock that correctly. And unfortunately, as the question a while ago, can you share the connection pool then between threads? And you cannot. The idea is that you one day should be able to, but that's a known bug. So today, curl 8.4.0 that we have released, the last release, and curl 8.5.0 that we will release soon, they still don't support cross threads connection pool sharing. So ideally, we will fix this at some point in time. So that's a little bit about the share API. Let's dive into TLS details. A lot of libcurl transfers, of course, use TLS, and all those protocols ending with S, protocol names, of course. And when you communicate with a peer, you of course want to use TLS, because TLS make everything better. That's an authenticated transfer, right? You're talking to the right server. The data is not tampered with, and no one can snoop on it. TLS is implied if you're using all these protocols, because then it'll use TLS automatically, pretty much, and you just use the correct scheme in URLs. And if you use one of these protocols in the scheme, FTP, IMAP, POP3, SMTP, LDAP, then you have to use this option that is called curl use SSL, which is pretty much because then you start out the connection, you start out the transfer without TLS, and then it'll negotiate TLS in line. usually with a command called start TLS or something like that. So upgrade to TLS while talking to the server. So typically you do it like this. For example, if you do FTP transfer and then you set curl opt use SSL and you say this argument says curl use SSL all, which means you force it on both the control connection and the data connection for FTP, since it has two connections. And important, fail if it can't. There's actually an option that says try it and continue anyway if it can't, which is a bad idea. Don't go there, because it's why try it if you allow a failure. So enable TLS. TLS is the way forward, right? You want TLS on your transfers. And I do this in a weird order here because I haven't really talked about proxy yet, but I will get to proxy in soon. And you want enable TLS, maybe, or at least if you have an HTTP or HTTP style server proxy, you want it with TLS there too, on HTTPS proxy, that is. And then you have a proxy connection that is controlled separately from your peer connection, right? So then you can set HTTPS / blah blah for proxies as well. And then you just do it like this. You specify your proxy and you say that your proxy is an HTTPS proxy. And then curl will do HTTPS to the proxy and then talk through that proxy to the remote server. When you do TLS, there's a huge set of ciphers and versions and things to use. And of course you can set those, but typically you don't need to care about that, because mostly when you use libcurl, it defaults to sensible modern safe set and it negotiates that with the server, right? So except in some very rare cases, you don't need to think about ciphers and TLS versions. But you can, of course, set them if you want to. And the proxy set is different. So you can, of course, set the server set of ciphers and versions to be different than the proxy set of ciphers and versions. And libcurl will by default always verify the server certificate, which is how you do it with TLS. So you need to make sure that you're actually talking to the correct server. And of course, you can switch that off if you for some reason want to. Typically, you should never do that in production, but maybe while developing, you want to switch it off because you do something crazy that doesn't really work the way you want it to. And also, libcurl, then when you build libcurl and when you use libcurl, it has a default CA store somewhere, typically on a file somewhere in your file system. And that is what it will use by default, unless you tell it to use something else with an option. And you can point it to somewhere else, and you can even provide, I'll show you in a second what I'm talking about. And you can do your own verification, right, with a callback if you want to. It's slightly complicated and it's very SSL library specific. So I rather advise you to try to avoid that. You can, again, the HTTPS proxy config is separate. So you accept and check the verification of the HTTPS proxy separately. You can also do pinning of the certificates as well. So there's a lot of options here. And you, again, sort of alluded to, never disable certificate verification in production. Therefore, it's typically you should avoid doing it while developing as well, because sometimes it risks just bleeding over. If you want to, we have this service on the curl website, and we've had it there for, I guess, 20 years by now or something. It actually provides the Mozilla CA certificate bundle as a PEM file. It's the conversion is done automatically. As soon as they change something, we provide a new PEM. So if you want the exact same bundle that Mozilla ships with Firefox, that's the PEM version that you can use with curl. It's usually more or less the same as the PEM file that is provided in Linux distributions, but not always strictly exactly the same. So all of those, not all, maybe most of those options that provide file names to different CA information and certificate information with libcurl, we have also blob alternatives, which is a way to provide, instead of a file, point to a memory block instead, memory blob. For example, if you're writing an application, you're having a device, something, maybe not a file system, maybe you want to have a build it into your application without any external files or whatever. And then we have these different sort of blob corresponding versions of the same options without the blob suffix. Cool stuff. And the blobs are just a struct with a data, a length, and a flag. The flag only has one purpose, and that is to say if curl should copy or not copy the blob itself. So you can actually, if you have, for example, if you have a blob that will remain in memory all the time, maybe curl doesn't have to copy the blob and have a separate duplicate of the data, then you tell it to not copy. Or maybe it'll go away from your application, then you can tell it to copy. And this is how it works pretty much. Just set up a struct curl blob, just initialize it to a pointer, a length, and you set the flags, and then you just set up the blob. In this case, the CA info blob. That's a certificate bundle, right? CA certificate bundle. Boom. Then you don't need to use an external file. Of course, it's using it this way then puts the responsibility on your application to update this every once in a while and so on. But hey, that's your job, not mine. When talking about TLS backends, I talked about this a little bit in part one about how curl can be built to use a number of different TLS backends, right? And this list on the right side here, where's my, there it is. The list up here shows 12 different TLS libraries that you can build curl to use. So either one or more of these libraries are used by your libcurl. I'm telling you this again, just because it's important to remember, because sometimes that particular detail bleeds into your use and what you can use and how you need to think about things in life. We make a really hard effort to make sure that the choice of TLS backend shouldn't really affect you, the API, or sort of your daily use of libcurl, but sometimes we fail at that. And there's one that is default, and you can build libcurl to use several of them, and then you can set which one to use when it starts up. So maybe you support 3 of them, and you can decide which one to use when it starts this time. And you can only set it at default startup time. I could mention, since someone mentioned the post-quantum ciphers. So post-quantum ciphers, like Kyber, is a property of the TLS library. There are several of these libraries that are already supporting post-quantum algorithms. So wolfSSL, for example, is a library that, I work for wolfSSL. We support post-quantum. So you can build wolfSSL today, build curl to use that, and you can go with all those post-quantum algorithms. And we've had that support enabled for years, actually. So you can, all of those post-quantum algorithms are there for you to start using today if you want them. They're typically not there by default, I think, in most of the TLS libraries. I don't know exactly why, but a little bit outside of my jurisdiction too. So if you're really interested in post-quantum algorithms and things, you need to sort of investigate that closer with the particular TLS libraries. But they're certainly coming, and there's going to be more about that. But you can already use them with curl today, and I don't think we need to do anything in particular with curl to change that or to make you able to use them, but you pretty much have to make sure that the TLS libraries support them. And this curl global SSL set is the way for you, if you build libcurl to support multiple TLS libraries, this is the one you use to pick another one. And you can only pick it at startup time, and you can only pick it pretty much the first thing you do. And then you're stuck for the rest of your application's lifetime. And the next time you start over, you can set another one. It's a limited feature. Maybe at some point in time, we will improve this, but it's also a really funky way to, And why would you change TLS library at startup? You tell me, you decide. If no animation on this slide. So of course, when you do things using TLS, everything you do is encrypted, right? So you can't snoop on the transfer. You cannot use tools like TCP dump or Wireshark out of the box and just see what's going on over the network, because everything there is encrypted on purpose, right? That's the whole idea with this, that you should prevent it. You shouldn't be able to snoop on it, but sometimes you want to do it anyway because you want to see what's going on. You want to track down a problem. You want to debug this, and you want to figure out what's wrong. And then libcurl supports the SSL keylog thing. SSL keylog file is an environment variable. So if you set it to a file name, libcurl will store TLS secrets into that file name while it is running. So while there's a transfer going. And this is actually an old thing that is sort of introduced by several of the web browsers. So Firefox and Chrome, I guess Edge also support it. So if you set that and then you fire up Wireshark and you configure Wireshark to say, hey, read my pre-master secret log from this file name, then you can use Wireshark to snoop on your encrypted network traffic in real time, even though it's fully encrypted over the wire, because you told libcurl to sort of leak the secrets for you so that you can use those secrets to decrypt the stuff over the wire, helping you to debug what's happening over the wire and understand stuff better. Pretty cool stuff, actually, and really useful, in particular in that debugging weirdo situations. So curl supports proxies, as I've already mentioned several times, but maybe I should also just hold back that a proxy is just basically an intermediary here, a server between you and the actual server you want to get to. So you send data to the proxy, and the proxy sends data on to the final server. Pretty much, here's curl, right? And in a regular situation, we talk to a website directly, like that, client to the server, peer-to-peer, right? End to end. But in this case, we have a proxy in between. That means that we have the proxy sits on network A. We communicate to the proxy communicates with the website over network B. So the client here, the curl client, doesn't really talk to the website directly or by itself, but only via the middleman, the proxy, the intermediary. In curl, we support two kinds of proxies in a number of different ways. And I made you this fun slide to show you. So you can go with either SOCKS or you can go with HTTP, those two proxy types, families of proxies. And if you go with SOCKS, there are two different sort of versions of SOCKS, one called SOCKS 4, one called SOCKS 5. SOCKS is a really ancient way to do proxy stuff. It is still used. SOCKS 5 is used by Tor still. SOCKS 4 maybe not so much by anyone, but still curl still supports them. And if you go with SOCKS 4, there are two different kinds of SOCKS 4. You can go with SOCKS 4 or the one called SOCKS 4a. And SOCKS 4a means that it won't resolve the hostname locally, but it will pass on the hostname to the proxy to resolve it. And we have the similar setup for SOCKS 5, that we can go with SOCKS 5 plain, or the one that I call SOCKS 5H. It is similar to SOCKS 4a in that you pass on the host name to the proxy to do the resolving. It's not resolved locally. For the other two, they resolve locally. I'll get back to that in a second. So, and if you go with HTTP, you go with either plain HTTP or you go with HTTPS server. That sort of just limits how you set up the connection to the proxy. And if you go with HTTPS, curl supports HTTP 1.1 or HTTP 2 with the proxy. So as you can see, just a bunch of different flavors, kinds, types of proxies. And all of these ones support local name resolve, which means that curl can resolve the host name and then just go through the proxy and let the proxy just connect to an IP address instead of a host name. All of these can do that, and here are the sort of the reversed ones. When you pass on the host name to the proxy and let the proxy do the resolving of the host name to IP. So it depends on what you want to do and who's going to be in charge of the name to IP conversion. In most cases, you actually want the red thing here when you want to pass on the host name maybe to the proxy and let the proxy do the resolving. But yeah, I'm not the one to tell you how to use it. I'm saying that these are the setups, and you can then typically you go with the one that works and exists for your use case. So typically you just don't make that up yourself. When you set a proxy, you set this option. It sets a host name, and you can set the host name with a scheme prefix, and the schemes are sort of made up by me. Or you can set the sort of the type of the proxy with this option. This is more of the older style. So you can go with either a scheme, host name without a scheme, or you set the type, and you can go with a proxy with a scheme. So like this, on the left side here are my sort of schemes, your proxy type schemes, and the right side is the proxy type name. So you can use either. I kind of prefer the left side myself, just to use the scheme and the host name, because it's sort of, then you put them next to each other in a URL-like way. I think that sort of think it looks better. And this is the way you do it. If you want to go through a proxy called local.example.com on port 8080, here it sets up the, and then it sets, proxy type is proxy SOX 5 here as a separate option. But if you wanted to instead of setting the proxy type option, you set the scheme version. So that's, then you can avoid one option and instead insert the SOX 5 scheme in the before the hosting, like this. Okay, easy peasy. That's proxies. So diving into HTTP. So with HTTP, of course, there are a bunch of different HTTP versions, and curl supports a lot of them: 0.9, 1.0, 1.1, 2, and 3. And who knows what else we're going to support going forward, probably more. And generally, you don't need to care, right? So typically you just go with HTTP and it'll just work it out by itself. But sometimes you need to care. And we have made an effort to make sure that everything from an application standpoint works as well, maybe not everything, but as much as possible, it works the same. So you don't have to care about which actual protocol it ended up using. It'll deliver data in the same way to your application, and you will provide headers and data to libcurl in the same way, independent of which of the versions that are actually being used in the end. 0.9 is actually more of a way of defines how a server sends data back to you, and that's more of an old ancient way that we're trying to discourage. So curl will actually not support that unless you ask for it, because it provides data in a sort of an unsafe way. We don't really know that it's HTTP anymore. So anyway, if you really insist on talking to a server that says it is a 0.9, tell it it's okay by doing this. Or if you want to go with 1.0, you just say, well, I want to have this, or 1.1, blah, blah, blah. Or you go with HTTP 2, which is the default when you're today, if you're trying to use HTTPS. It's going to 1.1 is the default if you're not using HTTPS, if you're using plain HTTP clear text, because there is usually, well, problems. Going with HTTP 2 over clear text HTTP can be problematic and error prone. So I would advise you to try it out first before you do it. HTTP 3, still experimental up until the most recent release, maybe not soon, but you ask for that by setting HTTP version 3, which will then try HTTP 3 and fall back if it doesn't work. Or you can go with HTTP 3 version only, which is a way to say, I'm going to do version 3 or fail trying. And just a reminder then what I'm talking about here. So this is sort of just my view of the HTTP protocol stack thing. You know, HTTP semantics is really the way we see things as a libcurl application. We don't really have to, everything is the same, independent of version really, but underneath, over the wire and what's actually going on underneath, there's going to be a lot of different versions and different mechanics on how to do the things. But let's not get stuck on that for too long. When you talk HTTP, there's a response code in the data that comes back, right? You're used to seeing HTTP 200 OK, 404 not found in anything. It's a 3-digit response code, and they are sort of divided into 5 different categories. There's an informational response that is it's a transient response. Actually, you get one more after this, and then there's a 200 series that means success. There are different kinds of successes. There's a 300 that's typically redirections. 400 that are client errors. The client did something wrong or unacceptable that the server didn't like, so it told you about it. And it's the 500 series, which is really a problem in the server side. It's nothing the client did that caused it, so it's fault is in the other side. And what I'm coming to here is that libcurl returns OK for a successful transfer independent of the response code. So it doesn't really consider the response code as part of the transfer, because it's just a sort of a property of the protocol. It's not sort of saying if the transfer worked or not. So even if you get a 300, 400, or 500 response code back, the transfer will still be considered OK. So the transfer is independent of response code. I understand that this is sometimes, I don't know, considered a problem, sometimes not. But this is just a fact. You just have to accept it, like it or not. This is just how it works. And it's been working like this since the dawn of time. So pretty much, if you do it like this, if you do a transfer here, that using a URL for a page that doesn't exist on the website, and you perform that transfer, and then you extract the response code. And in this example, we show the result from the transfer, the return code from curl easy perform, and we output the response code. That's the response code then that we get back with this HTTP response. This is what the example will tell us. The result is 0 because it's going to be a successful transfer. So nothing to be alarmed about. It worked, but it returned a 404 because the page didn't exist on the server. So the server returned a 404, and I'm just trying to stress that they are separate. The transfer worked, but it returned a 404. Redirects is a thing that is commonly used in curl, not in curl, well, in curl too, but I meant in HTTP, which is a way for this server to say, this resource is not here, it's actually over there. Or maybe not here anymore, and it could be there for a while, and so on. It's a response code that is 30 and the number, and the location header in the response headers. Curl, of course, does basic transfers by default. It doesn't follow redirects by default. You have to actually ask it to do it by setting this option, follow location. Location then being the header that says the new target, the new place where the resource now exists, supposedly. And pretty much you just set it, you just enable follow location, and it will follow locations. Redirects by default. Well, it's not by default. You asked it to follow it. So, or then it will actually follow any number of, it will follow many redirects when you tell it to follow redirects. And the number of redirects that it will follow is a separate option that you say, the max redirects option, so it's separate from this. And it has a default value, so it will not get stuck in forever land if you do it like this, at least not with a modern libcurl. With older ones, you could get stuck in a loop. So the method we're talking about here, the HTTP method, is the one that's called get, post, put, blah, 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 right? And when you do a download with curl, a download transfer, it will use get, because, and you know, download is the default transfer with libcurl. So get is the default method libcurl will use. You don't ask it to use get, it will just use get implied because you're doing a download. And if you're doing an upload, or if you're setting one of these particular options, it will do a post, and then it will use the post method. And similarly, it will then use put if you ask it to do a curl up upload. So you don't, typically the method is implied by the option you're using. You don't need to set the method. You can change the method curl will use by force, by setting this curl up custom request. Maybe funnily named, but still. Typically, you don't use this because the method is implied by the option you're using. You're typically just complicating matters by trying to outsmart curl by setting a method. Because really, don't set the method, because setting the method means this is the method we're going to use on all transfers with this handle, right? And if, for example, when you're following redirects, sometimes that follow redirect should change method. But since you have told curl to use a particular method, your wishes will override the redirect. So yes, this is the -X option with the curl command line tool. So there are instances when you want to use this, but pretty much never forget post put. So, or at least think it through properly before you do that. And if you want to go with redirects, following redirects at the same time, yeah, then you end up in a really funny situation. If you want to do HTTP post, post is a way to send data to a server over HTTP, right? One of the upload methods. Doing uploads over HTTP, there are many ways to do it. So HTTP upload is also always a strange sort of scenario because there are so many different ways to do it. But typically, you provide post fields as here's a buffer to send to the server, buffer of data. It's usually 0 terminated, but if it's not 0 terminated, maybe you want to send the JPEG. You also tell libcurl, here's the size of my buffer that you should send. You can also tell curl to, because this is the post fields option is the only option that you point to a string that libcurl will not copy by default, because you might send a very, very big chunk of data, so maybe it shouldn't copy it. But if you want libcurl to copy it, then you use curl opt copy post fields, and then it will copy it. And then you need to be sure to set the post field size as well, so that it knows how much to copy. You can also ask it to read the data instead of setting post fields, which points to a buffer, the sort of the convenient way many times. You can also use another way to do it is to use a read function, the way I showed you before on slide 16. That's like an hour or so ago. And then you tell it, so then you set the curl up post option and set the read back, because then you tell curl, here's a post, get the data from the read callback, and then it'll just work. And of course, the third way to do a post is to set the curl opt mime post option, which is the way to do structured sort of multi-part form posts. And I'll show you in how to do that in 20 seconds. I just wanted to show you the very short example how to do a post fields. This sends a short and sweet post to a server. You just point out the string to send, name equals Daniel, slides, yes, title, mastering libcurl. Blam, then it'll send those, 34 bytes to the server in a HTTP post. Voila, done. There's this concept of HTTP multi-part form post, which is a structured format to send a number of parts of data to a server. That's typically set with a content type multi-part form pass, multi-part form data. And that's a number of parts, name and content. And each part has headers, could have file name, and they're separated by a MIME boundary. So basically, this is an example of a two-part multi-part form post. The first part here is called name. It sets name to person, and anonymous there is the content of the first part. The second part then has name secret. It has a file name called file.txt. It has a content type, and then there's contents of the file. It says there on the screen. It's the actual content of that part. So two parts in a multi-part form post. And curl has an API that helps you create this kind of multi-part form posts. Typically, multi-part form posts are used by websites when you want to upload when you upload files, images and stuff. This is typically the method used. And you can do this with a libcurl, and it has this curl MIME API. It's called MIME because the format there is a MIME format. And you can also actually use this to send emails with curl's SMTP support using this. But anyway, so then the MIME post wants this curl MIME pointer as an argument, as a handle to a MIME post, right? So you want to create that MIME post that's one or more parts. And you do this like this. You create first MIME in it. It creates a handle, right? Curl MIME handle. You recognize the pattern, creates a handle. And on this, because that's manages an entire multi-part, many parts. So you add parts. It starts out with no parts, right? So you add a part. It has to be at least one part. So you add one part, add part. And that gets a handle back. That's a handle back to that first part. And that first part, it needs a name and it needs data. Name and data, that's basically at least what each part needs to have. And you set those with curl MIME name and curl MIME data. So you set the name and the data for that part. And then you add another part. Basically just wham, start over. Add part, add part, add part, add name, add data, add name, data, name, data. And there are also then a few other helpers. Then if you want to set the data in different ways, or set some metadata for those different parts, there are some additional functions. For example, you can set the file data. It's a sort of insert data from a file, or you can insert data from a callback. Just different ways to make more customized multi-part form posts. Really powerful stuff. It makes it really possible to do complicated multi-part form posts. When you do an HTTP request, there are a set of headers, right? So there's a method, there's a set of request headers, there's a possible request body. Those request headers, there are a set of the request headers that are sort of inserted by libcurl itself, sort of the bare minimum headers, the headers that needs to be there for the transfer to work. Typically a host header, an accept header, and yeah, pretty much that. And curl offers this option called curl up HTTP header that allows the application to change the set of headers used in a request. You can add headers, you can change the headers curl itself adds, and you can remove headers that curl itself adds. And I wanted to just show you an example. If you go from the top here, it says add a custom one. It adds a header that wouldn't exist otherwise in the request, shoe size :10. Just a silly header, just to show you how to add a header to the request. And in this case here, we remove an internally generated one because, as I mentioned, curl will use an accept header by default. But maybe we don't like that, so we can remove that from this request by just providing a header accept : no content on the right side of the colon. Then it will just remove this header from the request. And we can customize a header that would otherwise have been done by curl. Always makes a host header by default, right? But in this case, if you can change that. to another one, so that it will customize the one. So curl's internally used one will not be used, but this one will be used instead. And as a special case thing, you can also provide a header which just doesn't have any content on the right side of the colon. And if you check that, it's a little bit magic, but because it uses a semicolon in that string there. Because typically a header cannot be, at least the original intent of the headers, it was that they shouldn't exist without content. But apparently some people invented ways or times when you want that anyway. So curl has support for that, using this a little bit awkward way, but still it works. You can also do powerful things like, I just want to get that resource if it's newer than or older than a particular time. We support that with the curl up time condition. And you can set the particular time to talk about with the curl up time value large. It works for a few protocols, including HTTP, and you do it like this. This particular timestamp, as you can see here, 16987932000, happens to be the November 1st, 2023. Maybe at midnight. I don't remember exactly. And if you want to ask for the, I want to get the resource only if it's been modified after this time. If modified since, then this is how to do it. And if it's not been modified since, a HTTP server will return a 304 instead and say, nope, still the same. But then you don't have to download it again because maybe you already have that. So you save yourself a download. And I mentioned the ranges already before. I'll just show you again. And when it comes to HTTP, it's a little bit annoying because the server might actually ignore you asking for a range. So, hey, I only want byte 200 to 999, like in this request. But the server might deny you that and give you the entire thing anyway. Which, of course, might not be what you want, but hey, that's life. Put is a separate way to do uploads. Separate from post is more of a way to send the data to a resource on the server. Put is more replacing a resource, more of an actual upload of data, upload of a file, perhaps. And you do that by setting the curl up upload option, and you provide a read function callback, like this. In this case, we have a read callback in the top called read_cb. It just makes an f read, so that populates the buffer with data. You remember I mentioned how that we do callbacks. So if we want to upload data, curl will call the read callback every time it wants to read data to send to the server. So it will call this callback over and over and over until it returns end of file, and then we're done. Typically, you also want to set the size of the uploaded file ahead of time because it makes things better, but I didn't do that in this example. Heading into cookies. Cookies is a HTTP thing where we send name value pairs from servers and then back again from the client to the server. And they are set for a specific domain and a specific path. And they are, of course, only sent back to the server when the resource, when the conditions apply. Curl doesn't support cookies by default, right? Because it's basic by default. You have to ask libcurl to, hey, talk cookies here with this server. So you have to enable what we call the cookie engine. And when you enable the cookie engine, cookies are held in memory, and it will just deal with cookies automatically, correct. Save them in memory and send them back in subsequent requests when they match, and there are cookies that match the conditions. So basically, you set input like this to curl. For example, you can ask curl to read cookies from this file because you can, save them, of course, across sessions or through days or who knows, copy them from another machine. And you can also ask curl that, hey, when I read cookies from this file this time, consider this a new session. Cookies session. Cookies can be session-based. It means, if this is a new session, don't remember any session cookies from the previous session. That's basically what it means. Throw away session cookies from the previous session. And you can also, if you want to set a specific cookie, you want to say name equals Daniel in this particular request, then set it. Rarely what you really want, but you can do it. And you can also ask curl to save the output in a cookie jar. That's a file name to store the stuff when you're done. When you're done, save all the cookies to this file so that we can use it in another session, maybe tomorrow, and read it back again with the cookie file argument, the option. So this is how you control cookies. And cookies are stored as in memory, I told you, in the easy handle. And they are not shared between easy handles unless you specifically ask curl to do that. When you use cookie file or cookie jar, the options, you start the engine. So you can just tell it to use a 0-length file name, for example, to start the cookie engine without reading from anything. There's a similar thing, that's cookies, right? And there's a similar thing that is held in the easy handle, and that's a cache for alt service data. Alt service is it's a response header from headers. It's a response header from servers that tell the client that, hey, my service is also available somewhere else for the next n seconds into the future. So curl then saves that knowledge. This service is also available at another host name supporting these HTTP versions for a while. So for example, example.com 443 might be provided by another example.org 8765. And so the next time you connect to example.com 443, curl might actually then connect to the other site and the other port number, because that's what the alt service cache said. This is the original way and documented, specified way how to bootstrap into using HTTP3. It's a typo there. So because the alt service header also says which HTTP versions that is supported on this other host. The unfortunate thing is then, of course, that this works best for the next attempt, because you've already done an attempt, right? You already got a response now, so it's too late for this particular request. But curl saves this in memory, and it can be saved to file, and you specify this with an option, of course. And you specify to curl which HTTP version you want to follow. Basically, you do it like this. So you set the curl opt alt service, specify a file name to use as a cache, and you specify which HTTP options to support when following this with this option. And here's just a quick example. It sets, I want to go with H1, H2, H3. That's HTTP1 and 2 and 3, of course, you understand that. And you specify which file name to use as a cache for alt service data. Wham, and it'll just automatically save the cache at exit, load the cache on entry, and use the data to go to these specified HTTP versions in case you support them, and in case the server actually says that their service is available over those versions. Quite similarly, the HSTS thing is similar in spirit, I would say. HSTS is this strict transport security header that a server can send back and basically say, don't access this host name over clear text HTTP anymore for the next n seconds. That is, go with HTTPS only for this amount of time into the future. And this cache is also then kept in memory and can be saved and loaded, and it'll then just make sure that curl will not access that host name over clear text HTTP, but will internally redirect to HTTPS instead. And you use that pretty much the same way I showed you alt service, but this has some additional callbacks. So basically the idea here is that you can pre-populate this cache easily by using these callbacks. So, example, if you have a number of domains that you know will never be available, should never be accessible over HTTP clear text, you can pre-populate that header, that cache in your application using these callbacks. But anyway, oops, it's a broken example. So this example, if you pretend that you replace alt service with HSTS instead, yeah, okay, no, that example is broken, sorry. But it's you can read up in the documentation instead and see it. I should be able to fix. If you go to the GitHub repository for the examples and check the example, I will have that fixed by the time you do it. So I talked about HTTP versions before and how you can set different HTTP versions, and I would just wanted to come back a little bit with HTTP 2 because this is one of the ways to do multiplex transfers, right? HTTP 2 is, of course, then I said, should be transparent to the application. You get and send data the same way, and libcurl will default HTTP 2 over HTTPS unless unless you change it. But that's the default thing. And if you do that with the multi-interface, libcurl will multiplex or can multiplex if the conditions apply, right? And it also has a few extra options for you to set the dependency tree and the priority in old style HTTP 2. Not really a way that is encouraged, but it's there and you can use it. Very similarly, HTTP 3, it's not used by default. You have to ask for it, so it's not magically going to use it unless you really know that you want to use it. And it's only going to ever be used. You can only use it over HTTPS. There is no clear text version of it. And if you ask for HTTP 3, that means try it, and please try it, and it'll fall back to HTTP 2 or HTTP 1 as necessary in case 3 is not fast enough. Unless you say, hey, I only want to do 3 and nothing older. I can't really understand why you would do that, but maybe there are occasions when you want to do that. And HTTP 3, then as well as HTTP 2, can multiplex if the conditions apply. Recently, or at least within the last, I think, a few years, we have added this fun thing called the header API. Basically, headers, as in response headers for HTTP, is a information source that a lot of applications actually want to access in different ways. And traditionally, we only provided header callbacks that forced applications to do a lot of header parsing, and that's complicated and error prone. And then we introduced the header API instead. So pretty much this is a way for an application to get the details from a header, HTTP response headers. And you can use these functions in callbacks. So yes, this is an exception again to the regular rule that you're not supposed to use libcurl from callbacks, but you can also use them after a transfer, and you can enumerate all the headers, or you can get a specific header. And I will show you some examples because it's really easy to use and it's really powerful in case you want to get header data after or during a transfer. Pretty much like this. You do a transfer to get the https://curl.sc URL. You do the transfer. Hey, I wanted to know what was the content type that I got in this transfer. And then you're using the curl easy header like this, the easy handle, the header name, and there's a 0 here that's an index, and there's I want the regular header, I want the last header, and I want it stored in this pointer. Sorry, this is actually, yeah, this is then a pointer to a struct curl header. Little bit complicated, but I'll show you. Here's the prototype to the curl easy header function. It then wants a handle to the easy handle, of course, that's the transfer you just did. You want a name of the header we're talking about. You want an index, because a number of headers can actually occur several times, right? For example, cookies, you can have many set cookie headers in the same response. So this is the index, and it's 0 index, right? So 0 is the first one. Many headers, you can only have one, so then it's a 0 index. Origin explains what kind of origin the header is from, because there are a few different contexts where you can get a header. I'll show you in a second. And then even more complicated, if you're asking for redirects, for example, or you're using authentication, you could have gotten a number of responses in a single transfer, and this is the number of the request number. And then we have this shortcut that if you're using -1, it means the most recent request. So if you're doing redirects, this is the last redirect, or the response to the last redirect. The header data that comes back, that you get as pointer to one of these structs, is one of these curl_header structs. Name, value, how many headers that exist of this header, how many in this origin, the index of this particular header that you just got, the origin where this header is from, and then there's a secret anchor that is not due to touch because it's just a special thing that curl uses to know internal details. The origins, that means that where the header comes from. It's a typical normal header. That's a normal, just a HTTP response header. It could be a trailer, which is not a header, it's a trailer. That's actually a header-like thing that comes after the content. It could be a connect header that is actually a header that comes from a proxy interchange. Or it could be a 1xx header, which is a header that comes from one of these transient response things that comes before the real response. It's a little bit weird. Or it can actually be even a pseudo header. Pseudo header being special headers that comes with HTTP2 or HTTP3. They are prefixed with a colon, and they're special. So curl supports these 5 different origins of headers, so you can actually get headers from any one of these, or actually from all of them. So, and if you don't know exactly, in this example, I ask libcurl, hey, tell me the content type header from this transfer, because I know that servers typically provide a content type, but maybe you don't want that. Maybe you just want to see, hey, what are all the headers that we got back? Because you want to iterate through them somehow or do something. And then you can use the curl easy next header instead. It works in a similar way. You iterate through that and you pass in the previous header, and it can iterate over all the headers that we got. And again, this is reusing the same. You use origins again. You use the curl header struct again. So you'll get headers back the same way. So using this way, you can probe and really interrogate and get all the details about headers from the previous response. And here's the prototype for the curl easy next header. The easy handle, the origin, the request number, and then the pointer to the previous header that you asked for, so you can iterate through them. Really nice API, I think, powerful for applications. Another thing that we also introduced, I think this API was introduced in 2018, so maybe not new, maybe 5 years, but okay, newish in libcurl standards, the URL API. Soon, through the years, we realized that mixing URL parsers is really dangerous and hard for applications. So you shouldn't mix URL parsers. You should use one URL parsers. And if you're in an application, if you have to parse URLs and you're using libcurl, why not expose our URL API so that your application can parse URLs the same way as curl does? And then sort of reducing the risk that one parser would treat the URL differently than the other parser, because you would use the same parser for your application and for libcurl. And even if you didn't have that sort of need, being able to parse URLs effectively is a really powerful thing. So we introduced this, and this is then the same parser that libcurl is using internally. So we know that the parser will be used the same way if your application uses it as libcurl does. It supports URLs in the what I call RFC 3986 plus, because it's based on the RFC 3986, but there are some extensions that we have sort of felt obliged to support because URLs is not really a standardized thing anywhere anymore since a long time. So parsing a URL is a little bit of a black magic thing. So yeah, we try to stick to a standard, but we have sort of felt the need to bend the rules at some times because of the browsers are using a different standard. They call it the WG URL specification is a living standard, though, so it keeps changing. And it's not completely compatible with the RFC 3986. So we're in a weird position where things sort of don't always interoperate. Anyway, we're sticking to the old way because we want to support the URLs we always supported. So we're sticking to that. And with our curl URL API, you can parse URLs, you can change URLs, you can generate URLs, you can normalize them, you can do fun things. And we have this concept of, again, handles. So with the URL API, you have a curl U handle, and that represents a single URL. You create the URL handle with curl URL. And when you have a URL handle, you can do things with that handle, and you can duplicate it and get a new one based on the old one. So it sort of inherits all the properties of the one that you duplicate. But anyway, you set and get parts, that you set and get URL parts in this handle. Pretty much, you set the one you want to add or replace, change, and then you get the one you want to extract. And what is kind of fun here is that, okay, here are all the parts in a URL. I've tried to use I should just hide myself or do that first. I tried to use the names from the RFC. So the scheme from the left, the scheme, user, password, they're actually, okay, never mind. And then the host name, there's a port number. I call it 1234 here, but I wanted it to look like a URL, not. And then there's a path, there's a query part, and there's a fragment part, right? I think there are a few more parts that I'm sort of not showing on this example. But anyway, they're called like this. They have defined names in the URL, in the API. Curl U part underscore name, and the names are like this. We have this magic part called URL. It's actually every part put together as a URL. So it's a shortcut for everything, right? So these are all the parts the URL API supports: URL, scheme, user, password, options, host, zone ID, port, path, query, fragment. You can set and get all those parts. If you set the URL, it will parse the URL and divide it, split it into these different components accordingly, depending on the URL. If you get a URL, you get the entire thing that is set in the handle. And you can get and set individual components then as you see fit. You can, so if you want to parse a complete URL, you set the URL, like, and if you want to get it, you get it. So if you want to parse a full URL, https://example.com, you set it into the URL handle like this: curl URL set, the part is URL, here's the URL, blah, blah, blah. The 0 there, the fourth argument, is a flags. It's a bit mask. It actually has a bunch of features and options you can ask it to do, encoding it differently and treat it differently depending on different things. And when you have parsed a URL, or you have a URL handle, you can get a URL back out of that using curl URL get. And in this example, we get the URL back. And by doing this, we also get a normalized version of the URL, right? Because it will do things, it will lowercase the scheme, it will maybe add the port number, it will remove dot sequences from the path, it will blah, 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 stuff like that. So it will be a normalized version of the URL, and then it will show it output. And you can set individual components in the handle and then get the full one out. So if you, for example, you can create your own URL like this. Here, it creates a URL handle first, right? And then it sets the scheme, it sets the host, it sets the port, it sets the path. So it sets HTTPS as a scheme, curl.sc as a host, 443 as a port. Caveat here that is, it sets the port number as a string, because all of these set strings. It's a little bit odd, maybe, but just live with that. And then you set the path /index.html. All of these also, of course, has that 0 because they take options. You can do funny things, but I kept things simple in the example. And then you do a URL get out of this. Then you get the full sort of the complete URL that all of these components created, and then it outputs it. Wham. In this case, it works like this. So if you build the example and you run it, and then you get the complete URL output out of it. So by this, your application doesn't really have to know much about URLs, syntax, or standards, or anything. You can use this API to extract components and put components into URLs. So basically, if you want to get a part, for example, if you have a URL like this, you set the first one here, example.com:8080/donkey.php (h = 7. And then you can do things like, I want to get the port number out of this URL, and I want to get the query part out of this URL. Then you just do that like this. And of course, showing how that would work if you would build it. You get 8080 as the port number and got h = 7 because that's the query part from the URL. Your application doesn't need to know how the URL works, but the API does it for you. And it also has this funky thing, so you can ask it how a redirect would work. Basically, if you have a URL and you have a relative URL, sort of from this URL, you add this, go to this relative URL from this first URL. Where do we end up? So you set an absolute URL, then set a relative URL like this. First one, curl.sc/this/cool/path/here.html. That's the first URL. It's a long absolute one. And then you redirect to this second one. That is, in this example, is ... /second/take/move.jpg. Where does it end up? What's the new location? Yes, the curl URL API will do that for you. So if you build this example and run it, it'll look like this, because those ... // things are, removing things right from the right, going upwards in the hierarchy, ending up with /this/second/take/move.jpg. Convenient if you want to do redirects, sort of machine things before actually doing them in live or in real world. The API also provides URL encoding support, so you can sort of encode or decode things at set or get, which can be convenient. For example, in this case, a slightly convoluted example here, but you might want to go to the examples and see this in real life. But pretty much, if we look at the main, if we ignore the show path above in the top, the function first, and go down to the main, you see that we set the URL first. Example www.example/%20 works %3f/here blah blah blah. And then it will show the different parts here. Anyway, to do a long story short here, it shows that it can URL encode and URL decode parts on get and set, to sort of, depending on what you want and what you have, and you want to put into the URL and so on. You can ask curl to decode URL encoding or encode URL encoding. And just as a reminder, URL encoding is this % thing, right? So everything that's not pretty much that is everything that is not a valid URL character is encoded as % something. For example, a space becomes %20 in normal cases, because it's an hexadecimal ASCII number. And you can also do a similar thing with IDN names. So, IDN, international domain names, is if, for example, I'm using this silly example because it's in Swedish. It's called räksmörgås in Swedish, raksmörgås.se. And pretend that I know how a non-Swede would pronounce it. But anyway, it's an IDN hostname. So we should set this hostname with curl, and it supports IDN. It will automatically convert this to, well, if you want to convert if you want the hostname converted to Punycode, which is the, decoded version of the IDN name. So it's not seen like using the IDN letters anymore. You can do this. So instead of then seeing the räksmörgås hostname there, you got the Punycode version. And the Punycode version is, of course, the actual hostname that will be used in DNS and so on. Which is just convenient if you want to use DNS, or if you want to, whatever you want to do with it, since this is what's going on under the hood when you're using an IDN hostname. Anyway, so so if you would do libcurl transfer to this hostname, libcurl would of course do this itself under the hood. And you can also do the reverse. So if you set this Punycode version hostname in the URL, you can actually ask for the IDN encoded version. So it'll do the encoding in the other direction. So you would go back to the IDN version, assuming, of course, that it's actually a valid hostname. That is possible to do that. In both these cases, you can, in particular in the latter cases, at least from Puny to UDN, you can, of course, break that by providing a hostname that is not an IDN hostname in the beginning. So the conversion might not actually work. Still, you can do this, and it's convenient if you end up with a Punycode hostname and you want to go back to maybe display the IDN version for a user or whatever. It supports it. So quite a powerful API, I'd say. I'm very happy with the URL API because it's been proven really useful and powerful. Okay, we are approaching the end, and I'm way over the time I expected it to be, but okay, we're sort of over the hill now. It's sort of going a little bit slower now. I'm not going to get into the WebSocket API much. I'm just going to say and emphasize that the WebSocket API is still experimental. It basically is oriented around the WS receive function and the WS send function, so you can send and receive WebSocket data in a more in a pretty powerful way. And if you want to see more about this, you should really see my special extra stream and video I did about WebSockets with curl on June 16th. So that was a while ago, 5 months ago I did it. Of course, there's a link, there's a QR, or you can just Google WebSockets with curl or search for it on YouTube, and you can see that. It's a 45-minute special, and you can go into, and as I said, it's still experimental, so it might actually change a little bit. We might tweak it, but it's working pretty good, and sooner or later it's going to become get itself not experimental. So we have reached the part where I'm going to say something about the future. Of course, first I just wanted to say that this is a two-part thing, and I'm reaching 2.5 hours today, 2 hours the last time, so a lot of content. But all of this is a lot of stuff. We have documented everything. I think we're up almost 90,000 lines of documentation in the Git repository alone, and we have the everything curl book. So there's a lot of code, documentation and code to read in case you want to, in case there was stuff you didn't quite get and you didn't understand, or maybe I didn't even touch it because I left a whole slew of things out of this presentation because I only have so much time and energy to talk about stuff. So there's definitely more things to learn and experiment with. And go ahead, and if you can't find the answer, go ahead and ask us. We're a big community. A lot of people are using this, so I'm sure that a lot of us can help out. And yes, here's the book. Here's the URL to everything.curl.dev. That's the book. We're trying to keep that updated. Maybe it's a little bit behind on the most recent things, but we should go there. And talking about the future, I just wanted to sort of just remind everyone that we've been doing this for a long time, and we've been growing and doing things, adding things really through its entire lifetime. And actually this year, 2023, is actually going to be one of the most development intensive years we've done in curl since almost 20 years back. So we're certainly not slowing down. We're doing things more and more, and development speed is increasing. Nothing on the internet is slowing down or, you know, stopping. So it's neither do we. And I just wanted to just say then that, you know, things keep changing and we keep things changing. So all the new ideas, new systems, protocols, concepts, protocols, versions, and we're just going to keep on doing this. So maybe if you see this video in a long time into the future, things might have changed. And you should be aware that even when you keep using libcurl now, you did it before and you will do it in the future, things will change because we will need to keep up, and we keep developing things and sort of adjust things according to what happens in the world. And what we do is to a large extent, of course, affected by what people want, where the internet and where the community wants us to be, what we want from internet transfers, right? Because libcurl is internet transfers, nothing else, but we do everything that is internet transfers. So if it's internet transfers, maybe we should do it in libcurl, or maybe if it's not relevant anymore, we shouldn't do it. And it's an open discussion always, all the time. What should we do? What shouldn't we do? And if you have ideas, if you have opinions, you should, of course, participate in that discussion and bring your ideas, bring your code, bring your complaints, bring your issues, bring your questions. And we will sort of, when everyone does that and we get everything into the stew and we let it cook and we make decisions and we go forward. It has worked out fairly good so far, but you know, we can always improve and do better. So yes, you can certainly help. It's open source. It's all of us. We're totally independent. We can do whatever we want. It's just code and all of that, right? And by this, I think we are at the end of part 2. Is there any questions? Is there anyone still awake? Thank you for enduring my presentation. I hope it was at least somewhat educational and enlightening.